Hello guys. So in this video we will be covering a total of 5 time complexity problems. Each of these problems are not that difficult, but these are important. These are basically common patterns that we see in different DSA problems. This is part 1. In the part 2 video, we will be covering a total of 6 difficult time complexity problems, which are not that common in DSA problems, but those are asked in interviews or your online assessment tests. Okay, so let's go with it. This is our first problem. This is a simple nested loop. There are two loops, the I loop, the J loop. The outer loop, the I loop, is going from 0 to n minus 1 because it is less than n. The inner loop is going from 0 to n because it is less than equal to n. Okay, so what is the time complexity of this particular problem? So let's figure it out. The outer loop is going, I is going from 0 to n minus 1. Okay. J, the J loop, is going from 0 to n. Okay. So 0 to n minus 1. How many terms will be there? Simple, n terms. From 0 to n, there will be n plus 1 terms. Okay. So from this we figure it out like, okay, outer loop is running n times, inner loop is running n plus 1 times. So what will be the total number of iterations? Total work. This is just n multiplied by n plus 1, which is n square plus n. Okay. Now if we have the total work, that is the total number of iterations, how do we get the time complexity? What you do is ignore lower order terms, ignore any leading constants, and whatever is left, put that inside the big O notation. That's it. This is the answer. This is basically n square problem. This is one way to do it, which is the more prominent, the common sense way to do it. This is the way that you should follow. Now what to do if you cannot do this? There will be problems in which it is not very straightforward. Okay, inner loop is running this much, outer loop is running this much. In that case, what you do, you just trace the entire algorithm or whatever it is. So let's do that. Let's do method 2, which is tracing it. Method 2. Okay. I is equal to 0, I less than n, I plus plus, same loop. Okay. J equals 0, j less than equal to n, j plus plus. Now we need to trace it. How do we trace it? Basically just go through the entire, whatever it is, whatever is the code snippet. Okay. So what I see is there is I is equal to 0. So I 0. Is I less than equal to n, less than n? Yes. Then j goes from 0 to n. Okay. So j starts with 0. J less than equal to n? Yes, true. So you will do your work, whatever it is. Okay, I will write that also, whatever we are printing. So what are we printing? We are printing I and j. I value is 0, j value is 0. Good. Then j plus plus happens, j becomes 1. Is j less than equal to n? Yes, it is. Let's assume some value for n so that we know when to stop. Let's say n is 3. We're going for n value 3. Okay. Is j less than equal to n? True. Okay, then print it 0, 1. Why 0? Because we are printing I and then j. I value is still at 0. J value is at 1. Nice. After that, j plus plus happens. J becomes 2. Is 2 less than equal to 3? True. So 0, 2 is printed. Then j becomes 3. Is 3 less than equal to 3? True. 0, 3 is printed. Then j becomes 4. Is 4 less than equal to 3? No. False. So what you need to understand is, for these values of j, when the condition was true, iterations happened. Okay, iteration was there. But for the last value, where the condition was false, the inner part, this did not run. Why? Because the condition was false. So the loop body will not execute. So there are only 4 iterations, these 4. So from 0 to n, j is going from 0 to n. Don't count this one. Okay, I'll erase. Okay. Now what happens next? Next, because j loop is completely done, now I plus plus happens. So I becomes 1. I becomes 1. Is I less than 3? Yes, it is. True. So j again 0 is 0 less than equal to 3, true. So basically now you will understand this entire j, whatever we did here, it will get repeated here completely similarly, but only thing will be that now when you print, I value is 1 and j will be exactly what it is. So j is going from 0 to 3. This is when the conditions will be true and something will be printed. So 1, 1, 1, 2, 1, 3. At the end, j value will become 4, condition will be false. Okay. Then same for I value 2. So I becomes 2. Condition will be true. Yes. Again, same thing. True, 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 false. But now I value is 2. So 2, 0, 2, 1, 2, 2, 2, 3 will be printed. Okay. So if I ask you what is the output of this particular code snippet, output is 0, 0, 0, 1, 0, 2, 0, 3, then 1, 0, 1, 1, 1, 2, 1, 3, then 2, 0, 2, 1, 2, 2, 2, 3. This is the output. But we are not interested in the output. What is the complexity? That is what we want to know. So let's think. Now that we know, we have traced it. Now we know, okay, for I value 0, there are a total of 0 to 3. So n plus 1 iterations. N value is 3. So n plus 1 iterations. For I value 1, again, n plus 1 iterations. Remember the last value of j, there is no iteration for that because the condition was false. Then for I value 2, there will be n plus 1 iteration. Okay. So from there, we get the idea. It is n plus 1 plus n plus 1. So n plus 1 iteration for the first value of I, then n plus 1 iteration for the next value of I. Then similarly, it will keep going up to whatever is the last value of I. So this one is for I is equal to 0. And this one is for whatever is the last value of I. Last value of I is clearly n minus 1. So n minus 1. I is equal to n minus 1. So how many terms will be there? I is going from 0 to n minus 1. For each value of I, we are doing n plus 1 work. So from 0 to n minus 1, there are n terms. So there is total n terms here. If there are n terms, then it is just n multiplied by n plus 1, which is n square plus n. This is the total number of iterations. Now, what you do, ignore the lower order term, ignore any constants, put whatever is left inside big O notation. That is your answer, n square. So these are the two methods to do the same problem, and you can clearly see the common sense method is much easier compared to the tracing method. Actually, tracing method is easier, but it is lengthy. Common sense method takes a little, little know-how, like it will take you a little time to get to it, get your head around it. But once you have it, it will make everything very easy. That is it. That is problem number 1. Okay guys, so this is the second problem. Again, this is also a nested loop. So let's see how to do it. So simple, there is an outer loop, there is an inner loop. Inside the inner loop, we are doing some constant work. So what I'm going to do is, I'm going to find how many times the outer loop is running. Then I will find how many times the inner loop is running. And then I will multiply both. That will give me the number of iterations, which I will then just put inside big O notation. So how many times is the outer loop running? Let's figure it out. Outer loop is I is equal to 1, I less than equal to n, I equals I multiplied by 2. So basically what this says is I is starting from 1, going up to n, and each step you are multiplying it by 2, which is this. Start with 1, go up to n, each step multiply by 2. So 2 into 2, 4, 4 into 2, 8, 8 into 2, 16, 16 into 2, 32. Keep doing this until you reach n. This is the series. What is this series representing? These are basically the valid values of I. So first I will run for 1. Then it will run for, you multiply it by 2, it will run for I is equal to 2. Then multiplied by 2, it will run for I is equal to 4. Keep doing this. The last value that it will run for is I equals n, because the equal to sign is also there. So it will run for I is equal to n, and then the loop will stop. So how many times the I loop, the outer loop will run, depends on how many terms are there in this series. If there are 5 terms in this series, then outer loop runs 5 times. If there are n terms in this series, the outer loop will run n times. So I need to find how many terms are there in this series. Let's do that. How do I find the number of terms? Simple. Just remember this. Number of terms is equal to number of steps plus 1. Okay. So this is actually true for any series in the world. Let's say I have this simple 1, 2, 3, 4, 5. Okay. How many steps are there? First step, second step, third step, fourth step. There are 4 steps. So 4 plus 1, 5 terms are there. True. 1, 2, 3, 4, 5. 5 terms are there. Okay. So we will make an assumption here. Let's say there are k steps. Okay. This is the first step. This is the second step, third step, fourth step, fifth step, and at the end there will be the kth step. Okay. If that is the case, then can I say that this value is 2 to the power 0? After the first step, I value becomes 2 to the power 1. After the second step, I value becomes 2 to the power 2. After step 3, I becomes 2 to the power 3. After step 4, I becomes 2 to the power 4. After step 5, I becomes 2 to the power 5. True, right? Because these are only powers of 2. So similarly, after step k, I will become 2 to the power k. Same. Based on this, I'm writing this. So I can say, just like 32 is equal to 2 to the power 5, in this case, I can say n is equal to 2 to the power k. Right? If n is equal to 2 to the power k, then I will just take log. Log base 2n is equal to log base 2 to the power k, giving me k log base 2 which is equal to k. For those who don't know, log base a b to the power k is equal to k log a b, and log base a value a is equal to 1. So by that we can say that from here we get k is equal to log base 2 n. So what was k? K was our number of steps. So number of steps is log base 2n. So number of terms becomes, number of terms is equal to log base 2n plus 1. That's it. So the outer loop runs this much time. So outer loop is log base 2n plus 1. How many times is the inner loop running? So inner loop goes from j is equal to 0 to j less than equal to n j plus plus. So basically going from 0 to n, each step increasing by 1. So this is a very simple series. Start from 0 going up to n. So how many terms are there? There are a total of n plus 1 terms. That's it. So the inner loop is running n plus 1 times. So now I have how many times the outer loop runs. I have how many times the inner loop runs. Just multiply the two. So the answer, this is actually the same. I'll just remove this. So the answer is log base 2n plus 1. This is how many times the outer loop runs, multiplied by n plus 1. This is how many times the inner loop runs. Okay. So this is basically not the answer. This is the number of iterations, total number of iterations, total work done. So we can basically do the multiplication here, or what we can do is to make our lives easy, we will start assuming here only. Okay, in this step only. Ignore any lower order term. This becomes log n. In this also ignore lower order term. This becomes n. Multiply the two. This is n log n. Now put inside big O notation. Answer is this, n log n. Okay. N log n is the complexity of this problem. And that's it. This was problem number 2. Let's see what is problem number 3 now. Thank you. Okay guys, so this is the third problem. Now, if we look at it, again a nested loop, right? So you would think, Okay, fine. Count the outer iterations, count the inner iterations, and multiply the two. Correct? Okay, fine. Just do it this way. Count the outer iterations. Outer iterations. So basically, I is going from 0 to n minus 1 because there is no equal to sign, right? So n minus 1, 1, 2, 3. At each step, we are just increasing by 1. So this is the series for I. How many terms are there? N terms are there. So okay, fine. Outer loop runs n times. Correct. What about the inner loop? You will think, okay, inner loop runs from minus 1 to 0 because here 0 is written, I plus plus happens. But that will be completely wrong. Why? Because we have to check properly. Look at it. What is the initial value of j? It is minus 1. So what will happen is, for I value is equal to 0, j will go, it will become minus 1. And then you check the condition. Is j greater than or equal to 0? No. So false. Hence, the inner loop, the j loop, does not run. Similarly, for I is equal to 1, again, j is initialized with minus 1, condition is checked. Again, it will be false. It won't run. Similarly, for I is equal to 0, I is equal to 2, I is equal to 3, 4, 5, up to n minus 1. In each case, every time, j is initialized with minus 1 and the condition is false. In each case, it is always false. Hence, in each of these cases, inner loop is not at all running. So, what is happening is, for I is equal to 0, the j loop is not running, but we are still checking things, right? We are initializing j, we are checking the condition. So we can say that for I is equal to 0, we are doing constant work. Similarly, for I is equal to 1, we are doing constant work. I is equal to 2, we are doing constant work. For each of these, okay? For each of these, we are doing constant work. So what will be the total work done? Total number of iterations or total work done? It will just be this O1 constant work multiplied by how many times are we doing this? I is going from 0 to n minus 1. So there are a total of n terms here. So we are doing this n times. So constant into n is basically just n. This is the complexity, big O of n. So don't always assume that if it is a nested loop, then it will be n square. Or if it is a nested loop, I will just multiply the iterations of the inner and the outer loop and just get the answer. You need to check. Okay, you need to be careful. What are the values written? Whether the conditions are going to be true or not. Only then come up with the answer. That's it. Let's move to problem number 4. Okay guys, so this is problem number 4. So this is a while loop. If we look at it, there are two variables. There is a, then there is I, which is initialized to n. And the while loop, the governing variable is always here inside the brackets. So we see clearly that I is the governing variable. I is the loop variable. Okay, why is this important? This is important so that you don't get confused with this line. This line is just some calculation. It has nothing to do with how many times the loop will run. Okay, so just check the value of I, how it is changing. So while I is greater than 0, I equals n. So I is starting with n. Okay, it is going up to 1 because it is greater than 0. So it is going up to 1. In each step, you're doing I equals I by 2. This is same as writing I is equal to I by 2. Okay, people from C, C++, Java will know this. People from Python will write it something like I equals I by 2, something like this. But this is just this thing. You're dividing I by 2 in each step. So you're starting with n, dividing by 2, right? So this becomes n by 2. Then it becomes n by 4. Then it becomes n by 8, n by 16. Keep going up to 1. So at the end, you will reach 1. This is the series. These are the valid values of I for which the while loop is running. Okay. So if we are able to find how many terms are there in this series, then we can say, okay, if these are the valid values of I, and let's say there are x terms in this series, then this means the while loop runs x times. And if I get that x, basically if I get number of times the while loop is running, I will just put it inside the big O notation. That will be my answer. Okay, let's do this. Try to find how many terms are there in this series. Now, here, remember one thing. This is one series, but we did problem number 2 in the same video. It has this same series just in reverse. What I'm trying to say is this. Going from 1 to n, at each step multiplying by 2. So 1, 2, 4, 8, 16. Okay, if this has x terms, then going from n to 1, each step dividing by 2. This will also have x terms. Think about it. This is just reverse of this 1, 2, 4, 8, 16 up to n. Right? So what I can say is, I is following this particular series. That is true for this program. But if I just want to find the number of terms, then what I'll do is, I'll just reverse the series. I'll make it like this. And I will find the number of terms in this series, because this one is easier for me. If I find the number of terms in this series, then that will be equal to the number of terms in this one. And hence I will get the number of times the loop is running. So 1, 2, 4, 8, 16, I've already done this in problem number 2. What you do is assume the number of steps. Let's say number of steps is k. Then you can write n as n is equal to 2 to the power k. And then you apply log operation on both sides and you will get n is equal to log base 2n. Sorry, k is equal to log base 2n. And if you have, k is the number of steps. If you have the number of steps, the number of terms is just log base 2n plus 1. Okay, this is the number of terms. So in this series, it is the number of terms, which is log base 2n plus 1. So this means clearly that in this series, number of terms is same, which is log base 2n plus 1. So now we have the number of terms. So this particular series, which contains the valid values of I, it has a total of log base 2n plus 1 terms. Hence, the while loop runs log base 2n plus 1 times. Okay. Now, ignore the lower order term, ignore constants, put inside notation. Big O notation, this is your answer, log n. Okay. So, from this, what do we learn? What do we learn? We learn that if the loop variable, whatever it is, okay, whatever kind of loop it is, for loop, while loop, do while loop, whatever it is, if the loop variable is increasing by a constant value, increasing by a value, okay, when I say increasing, I mean plus, okay, not multiply, plus, then complexity will always be big of n. Okay, why? Because if it is I plus plus, then it is simply big of n clearly. If it is I is equal to I plus 2, yeah, that is you're increasing by 2, then it is actually n by 2, but you ignore constants giving us big of n. If it is I is equal to I plus 3, then it will be n by 3, but then again you ignore constants, so it will give you on only. Okay, so whenever you are increasing a value plus, it will be big of n, or you're doing minus also. In that case also it will be big of n. You have to check the conditions, okay? Like it has to be a valid loop. So for I is equal to n, I greater than or equal to 0, I minus minus. This loop is a valid loop. So for this, the complexity will definitely be big of n. Okay? Even if I make it I is equal to I minus 3, in that case also it will be big of n. But if it is not a valid loop, let's say that this sign here is reversed, then this is not a valid loop. Okay? Because I is starting from n. If it is starting from some number, it cannot be greater, let's say n. Yeah. So in cases this can go bad, like, this loop can go invalid. If that is the case, then you don't have to, try to find the complexity. But what I'm trying to say is increasing or decreasing by some constant value using plus minus, this is all ends up always on. Okay. If it is increasing or decreasing by multiple, by some multiple, basically you are doing multiplication or you are doing divide. If this is the case, then it will be in some log. Okay, now what is the log? It will depend. Okay, if you are multiplying by 2, then it is log base 2n. If it is multiplying by 3, then it is log base 3n. But it will be big of log, because at the end you will also, ignore all the constants. So all that will go away, log will be only left. So big of log n will be there. So plus minus ends up at on, into divide ends up at log n. This usually happens. So always check the validity of the loop. Like for example, in this loop, I is equal to n, I less than 0, I minus minus. I'm assuming that n is some positive value. In that case, this loop is not going to run, right? It becomes invalid. So why would you bother checking the condition? Don't go and write big of n for this. No. This becomes a constant, because you will just check these two things and you will see, okay, the loop is not going to run. So the complexity becomes constant. Okay. So this is it for problem number 4. That's it. Let's see you in problem number 5. Okay guys, so this is the last problem, the 5th problem. This is pretty easy actually. I equals 1, I into I less than equal to n, I plus plus, simple loop, right? So, but what happens is people get confused with this part. Like they're not able to understand what will happen with this one. Okay. So what you need to do is, one thing is clearly you can start trace, I is equal to 1 is, and then for this one, the condition, each time we will have to calculate like 1 into 1 into 1. Is this less than equal to n? Yes. Then you proceed with the loop. And you keep doing this. This can work, but then it will basically end up being lengthy and very calculation intensive. Okay. So what do? Just use your head a little. What is it written basically? It is written I multiplied by I less than equal to n. If we forget about computer and just think in maths, this is basically I cube. I cube less than equal to n. So basically it is written I is equal to 1, I cube less than equal to n, I plus plus. Now again, still this is not helpful. Now what do? You take cube root both sides. This becomes I less than equal to cube root, right? So n to the power 1 by 3 cube root of n. So basically this loop is just for I is equal to 1, I less than equal to cube root of n, I plus plus. That's it. A simple loop. What will be the complexity of this loop? You're starting from 1, increasing by 1 each time, and going up to cube root of n. So n to the power 1 by 3. So what is the complexity? You're starting from 1, going up to some number, each time increasing by 1. So complexity is simply big O of this. How many terms will be there? If it is 1, 2, 3, 4, 5, okay, then there are 5 terms. So if it is 1, 2, 3 dot 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 x, then there will be x terms. So 1, 2, 3, 4 dot 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 n to the power 1 by 3. So n to the power 1 by 3 terms. Put this inside your big O notation. That's it. This is the answer. And that is it with this video. We solved a total of 5 problems. Each of them was unique in their own way, and this was good. But these were fairly, intermediate level. In the next video, the part 2, we will be solving 6 problems which are difficult problems. Okay. Let's see you in that video. Thank you.